Next, we create the field output requests. In the field output requests container, Abacus has gone ahead and created a field output called foutput1. Let's rename it by right-clicking on it and choosing rename. We'll name it selected field outputs. In the Edit Field Output Request window, by default, the domain is set to the whole model, and the frequency is set to every n increments where n equals 1. We're going to leave these set at the defaults. For the output variables, we're going to disable strains and contact, and leave the rest of them at the default values. We are not going to create any history output requests in this simulation. Our next step is to create the loads. In the Create Load window, set the name of the load to Force1. Ensure that the load will be applied during the loading step. For the category, choose Mechanical, and for the type, choose Concentrated Force. Then click the Continue button. Abacus prompts you to select the points for the load. Select the node inside the viewport. Click the Done button. In the Edit Load window, we're going to set CF2 to -3000. This is because we want a force in the negative y direction of 3000 newtons. We have no forces in the x direction, so we leave CF1 blank. Click on OK. Our new force, Force1, has been added to the loads container. Repeat the process for the next two forces in the negative y direction of 5000 and 6000 newtons respectively. Next, we create the boundary conditions. Double-click the boundary conditions item. Our first boundary condition is to pin one end of the truss. In the Create Boundary Condition window, set the name to pin. We set the step to the initial step. The category is mechanical, and the type is displacement rotation. Click the Continue button. Abacus prompts you to select the regions for the boundary condition. By holding down the Shift key, you can click both the nodes on the truss structure that you would like to pin. Then click Done. In the Edit Boundary Condition window, we're going to check off U1 and U2. This is to prevent translation in the X and Y directions. However, we're not going to check off U3 because we want to allow rotation in the XY plane, or rotation along the Z-axis. This gives us a pin joint. Click on OK. You notice that the constraints are displayed in the viewport, and that our new boundary condition has been added to the boundary conditions container. Our next step is to mesh the truss. When we instanced the truss inside the assembly, we specified that the instance would be dependent, which meant that the mesh will be on the part. So expand out the truss part in the parts container and double-click on Mesh. You are now in the Mesh module. Our first task is to set the element type. You do that from the Mesh menu by selecting Element Type. Abacus prompts you to select the regions to be assigned element types. Select the entire truss using your mouse and click the Done button. We set our element type to 2-node linear 2D truss elements. Click the Done button again. Now we're going to seed the edges of the truss. From the Seed menu, select Edge by Number. Abacus prompts you to select the regions to be assigned local seeds. Select the entire truss once again and click the Done button. We would like to have 4 elements for each segment of the truss, so type in 4 and hit the Enter key on your keyboard. We can now mesh the part by choosing Part from the Mesh menu. When Abacus prompts you to mesh the part, click the Yes button. The truss changes color in the viewport, indicating that it's been successfully meshed. And you see the message, 10 elements have been generated on the part at the bottom of your screen. Now we can create the job. In the Analysis tree, double-click on Jobs. In the Create Job window, set the name to Truss Analysis Job. Make sure that the source is set to the model and that truss structure is selected. Click Continue. In the Edit Job window, you can add a description of the job. Make sure the job type is set to Full Analysis and click on OK. Truss Analysis Job has been added to the Jobs container. To run it, you can right-click on it and choose Submit. If you've already run the simulation once before, Abacus might warn you that the job file already exists and it's going to get overwritten. I'm going to click on OK. Abacus runs the job and completes it successfully, as indicated by the word completed in parentheses. In order to view the results, you can right-click on it and choose Results. You are now in the Visualization module. You can view deformed and undeformed shapes of the truss structure by clicking on the View Deformed Plot and View Undeformed Plot tools. If you'd like to have both deformed and undeformed plots overlaid over one another, use the Allow Multiple Plot States tool. It's possible you might later need to read the output file and would like to know what the node labels are. To display them, click on the Common Plot Options tool. In the Common Plot Options window, go to the Labels tab. You can check off Show Node Labels and click OK. The node labels are now displayed in the viewport. Next, we would like to plot the displacement as a color contour. From the Result menu, choose Field Output. Choose Spatial Displacement at Nodes and Magnitude. This will display the magnitude of the displacements in the color contour. In order to display it, we set the plot state to Contour and click OK. Now let's try displaying the U1 component of the displacements, which is the component in the X direction. From the Result menu, once again choose Field Output. This time, instead of selecting Magnitude as the invariant, we're going to select U1 as the component and click OK. And now you see the X component of your displacements have been plotted in the viewport.